Welcome to the next part of our Marantz 250. Let's check the DC offset on the other channel. Of course, we rebuilt the first one. Let's look at this one now and see what we have. Power on. Well, I don't think that's something that we want to have on our speakers now, is it? So, looks like before we do anything, we're going to have to troubleshoot this channel. And then once we get it repaired, then we can go ahead and make the mods to this that we did to the other one. Now, before we start on this, let me make some comments on the video that I did on the soft start circuit, because I got a lot of comments on that one, and a lot of different, I think there was some confusion, so I want to set the record straight on a few things. Number one, this chassis mount resistor. It is a chassis mount resistor. Chassis mount resistors are meant to be mounted on a chassis. I had some comments of some folks that were a little concerned about connecting mains power to this. Let me put your mind at ease. We use these in the medical field on X-ray generators all the time, and even with 480 volt three-phase mains. Truth of the matter is, operating voltage on one of these resistors, and you can look it up yourself, is 1500 volts RMS. The maximum safe is going to be it's 1250 volts RMS. My bad, not 1500. 1250. The maximum voltage, the peak voltage that this can handle, insulation-wise, is 2500 volts RMS or 3500 volts peak. So the failure mode on this is not to short to the case, but rather to go open circuit. So the bottom line is that's not going to happen, and I have never seen it in any of the setups that that we've used in the past. And I've had some really nasty blow-ups happen out in the field with these, and it's never the resistor. They blow open. That's all that happens. They go open circuit. Now, I had a ton of comments about all these Rube Goldberg things you can do to modify this circuit. But the fact of the matter is, this is still the way to go as far as I'm concerned. A couple of you mentioned using thermistors or inrush current limiters and NTC ones, meaning negative temperature coefficient. They usually start out at at a few ohms, maybe 5 ohms or something, and when they heat up, it's basically a resistor. When it heats up, it'll drop down to maybe less than an ohm. It still puts a resistance in line with your transformer, but it's very low resistance. And I hate using those, especially in transistor equipment. Possibly vacuum tube equipment, because it's hot inside there already. But those things, especially with high current devices, such as these big transformers like this, large amplifiers, the only way they can deliver that kind of current and keep that low of a resistance is for them to run very, very hot. So they're like little space heaters. And what happens when you put heat with a semiconductor? You got it, it changes. That's why we go through all this mess with these bias circuits to make sure you have tracking and so forth. So I hate that. I hate using them. I'll never use them for this application. Some people do, and that's great. You can, but I'm not really into using inrush current limiters for that purpose. That being said, they have their place. Like, for instance, we have some real high wattage halogen lamps in some of the equipment that I work on at work. And those lamps last all of about 2 months before they burn out. Because when they turn on, there's an incredible amount of inrush current until they heat up and start to light up. We put those NTC thermistors in line with them, and that 2 months of filament life turns into over a year. So they do have their place, but those thermistors quite often will get all crusty and burned, and they'll even crack and fail. We have to replace them. So it's not an ideal thing to use for these. Now I know some of you all use them, and that's great if you like them. You're right, it will limit the inrush current, and you do not need the use of a relay. So just to reiterate that, I'm just saying my personal preference, I don't like them for that reason, because of the heat and all that other stuff. The other thing is, when they do go to their lowest temperature or their lowest resistance, it still imposes a resistance in series with the transformer. So there is still a little bit of current limiting there. More so than if you had just a direct set of relay contacts. Another thing was, a lot of you got hung up on delaying the relay longer for for limiting the current for a longer period of time before this comes in, or worrying about the contacts failing because of the arc flash when they close, or the relay doesn't close hard enough because of this resistor, all these things. You have to remember, this is kind of a feedback loop system. In other words, the output of this transformer is feeding what's going to drive the input of the transformer. What I mean by that is, this dropping resistor is in line with the primary of the transformer. The secondary of this transformer goes into the bridge rectifier, which is over here. That's these diodes. These diodes then begin to charge the capacitor. So the capacitors will draw really heavy current from the transformer. The transformer will then, on the primary side, draw heavy current through the resistor. Now, that's how it's supposed to work. Once this capacitor begins to charge, it has to get up to a certain level before the voltage across this relay will get high enough to pull it in. Now, this happens very quickly. And some of you think that that's too quick and that you're not really limiting the current. But you have to remember, this resistor down here determines when all this happens. Because of the way I selected this, this capacitor is charged to about 75 to 80% of its maximum voltage before this relay even pulls in. If that's the case, a capacitor doesn't charge linearly. In other words, the highest current draw that it's going to have is when it has the lowest voltage across it. Once the voltage begins to build up, the current begins to drop down. Once the current drops down, the voltage drop across this resistor goes way down. So when these contacts close, you're just clamping out a small voltage drop across here relative to what it would have been when it first turned on. If the capacitors are not charged up to the level they need to be, this will not pull in. It's a self-correcting circuit. So you don't need to worry about how long it takes to come in. It'll take as long as it needs for the voltage to come up before this comes in. And you don't need to worry about how much voltage drop there is across this, because by its nature, when the voltage is up to that level, the current is reduced, which means the voltage drop across this resistor is reduced, which means you're not shunting out that big of a voltage. So all in all, this circuit will work fine. And believe it or not, this is almost exactly the same circuit with different component values, that's all. The same circuit that they use in the Pioneer SX1050, SX1250, the 1980, the 1080. They all have the same thing. They use a dropping resistor going to the coil of a relay, shunted across the capacitor bank, that is set to such a value that the capacitors have to be charged up to a certain level and the current down to a certain level before the relay will come in and close out the this resistor here. So nothing to worry about. Hope that sets your mind at ease about all that. That's it. I did answer a lot of those questions in the comments, so you can read through those as well. But I just wanted to comment on that simply because of how much interest there was in this, and I wanted to make sure everybody was on the same page as to why I did this the way that I did. All right, let's get to our video and let's troubleshoot this thing. Okay, throughout this video, I am going to be changing up between the correct schematics, which is this is a first generation amplifier, and the second production run, which we're going to call that the mid, because they're just, you can see how much clearer these are to read. This is a much better print than this one. I could not find an extremely clear print of the original early version of this amplifier. So some of the values are smudgy and hard to read and hard to see, and they're almost identical to this. The changes that were made between these two, we can obviously see them, like the constant current source that they put in the diff pair, and some of the capacitors they used for the Miller capacitors, and a few things like that. But for the most part, they are very, very similar. So we can actually use the easier to read prints. So you'll see me bouncing back and forth, but understand the most correct one is this blurry one. And that's why sometimes we'll be using it. Now if you look, the output of the wiper of the DC offset, or the DC balance pot, goes through this resistor that I think it says 100K, and through this 1K, and then you can see it ties in here, and this is where it goes into your differential pair. And they're saying, I can't tell what that says, so now we're going to jump over to the other one, and see, this says it should be 0.3 volts. And remember, this one's different because it has a current source on it, and this one has a tail resistor as the current source. So they're a little bit different. But I think it should be about the same. So they're saying, I'm thinking this is going to be around 0.3 volts, and they're supposed to be the same. Am I right? Let me see here. Yeah, 0.3 volts. So we're going to go onto the base of the diff pair, and we're going to see if in fact that's where our problem is, because it could just be that this potentiometer is dirty and we just need to move it around. So let's check that out. Okay, we're going to look at the base of Q502. So let's see what that looks like. We'll put some power on. And yeah, look at that. We have like 15 volts, so that's way off. And that's on that side. Let's look on the other side. Be very careful here. I have the power turned off now, but there's still some voltage floating around. I don't want to short anything. Turn it back on. And it's 5 or 6 volts. So yeah, this is... the problem is clear up in the front end. Now we either have a bad transistor, or there could be something weird going on with this potentiometer. There's any number of things it could be right now. So we're going to look at that and see where this is coming from. Okay, let's check our power supplies. First thing we have here is we have a Zener diode here. So you have this dropping resistor, and you have another one down here, and you have these two Zener diodes referencing to ground. So you can see this one goes to ground, this one goes to ground. You can see they're turned around opposite directions. This one is for a negative 17 volt supply, and this one's for positive. So it's going to be anywhere from 17 to 18 volts. And that's if we don't have our plus and minus 17 volts, if one of those diodes has failed and allowed the voltage to go way up, it's going to cause that offset problem. So let's look at that first. And I currently have a current limiting on there just in case something decides to go crazy. So we have minus 17, and we have plus 17. So those diodes are good. And I can feel these getting just slightly warm, and that's all right. Now, feeling these, they don't feel, I don't feel anything overheating, nothing like that. All right, so let's look at our two diff pair transistors. On each side, let's see, we should have, the emitters should be tied together. And the emitter on this one is on this side. And there's your tail of your long tail pair. And the collector is on the other side here. And that's 17 volts, which that's what we should have, because here's your collector going straight up to your 17 volts. And then this other one should be a little bit lower. It should be 16 volts. So let's look at that. If I can do this around the camera, trying to see everything. And it is 16.9. So that's good. However, it's saying that we should only have about 9/10 of a volt on that emitter. And if you remember, that's way high. It's 14 volts. So these guys are turned on full bore. Now how can that happen? We can either have a bad transistor, or we could have another bad component, a transistor or something down the road, that is causing this. And I can feel both of these warming up. Of course they do. That's pretty normal. I don't feel anything. The power transistors are absolutely ice cold. I mean, like, not even like trying to get warm. So something's not right. Okay, so we have in our offset, we have this 100K resistor, which is R504. We have R513 and R519, I think that is. And these are 1% precision resistors. It's a 20K and a 1K. And then they go up, and that's what feeds this differential pair. And I found them on here. And here's the 1K. And if I measure that, it's pretty spot on 1K. I mean, it's not that far out. And if I measure the 20K, I'm reading across a capacitor, and it kind of drifts all over the place. I have a feeling it's good, but it is very difficult to read, so I'm going to have to take that out of circuit to verify it. And while I have this apart, I'm going to pull a couple different components, including these transistors, and I'm going to test them as well. Okay, we lifted the one side of the resistor. Now we can measure it. And look at that, 20K right on the money. So the resistors are good, which I kind of thought they would be. You know, they don't look burned up or anything like that, so that's good. So let's start pulling some transistors and checking them. Okay, checking the capacitor that was bad on the other side. Wow, that's horrible. And then these ones, they're bad too. Just like the other side, they're in just terrible shape. So, yeah, those are going to need to be replaced. And although I'm not sure if that's causing, of course, it caused us problems on the other side now, didn't it? Well, while we're at it, before we pull the transistors, let's look at our bias diode and see if it's all leaky as well. Okay, looking at this diode in the one direction. Okay, we're reading forward. And then let's see how leaky this one is compared to the other one. You could see very, very little reverse leakage. If I go to the times 100,000, which uses that 30 volt battery, you can see very little leakage for a germanium diode. So this is not the same Leak Master 2000 that the other side was, so I don't think that's causing our problems. We'll disconnect the transistor and we'll check it as well, and we'll see if it's bad, but I don't think that's going to be a problem. Okay, looking at our bias diode, or our bias transistor, and it is good. I don't see any problem with that. Okay, here's an interesting one. The transistors on the board pretty much statically checked out good. I checked them right on the board the same way that I did the other channel. So if you want to see that, go back to the previous video and you'll see how I checked those transistors. But this is really interesting. So these are the pair that goes on one side, and these are the PNP side. So, or I'm sorry, the NPN ones. So if I go from base to collector, I get my voltage drop. I get base to emitter, voltage drop. I go emitter to collector, it's open like it should be. I reverse the leads, emitter to collector, and look at that, 1.5 volt drop. Now that's kind of strange, so let's compare it with the other one, and these are both identical transistors. I'm holding this one upside down. And if I go collector base, collector emitter, and then I go emitter collector in both directions, and it's open. Now here's where I've never seen this little device do this before, but just for giggles and grins, I connected. So here's the good transistor. We'll connect it up. This is the kind of stuff that interests me when I learn new things. And if you look, this is a good transistor. It's got a beta of 68, and you can see VBE is 478 millivolts, how you would expect it to look. And if we go to the other transistor that read funny with my meter, it looks the same, right? Beta of 74, so it's a little bit better gain. But look at this. There's a little tiny picture of a diode up there that was not there on the other transistor. Now, strangely enough, if you didn't really pay attention to that, you would think this transistor was okay. But this actually shows that it thinks there's a emitter collector reverse bias diode on there, and that's what that's showing, I think. That's what they're trying to say. But that was very interesting. Long story short, we have a leaky transistor. And so if one of these transistors is taking a piss while it's trying to conduct, well, definitely not going to work. So we're going to have to replace these. And we'll see if that makes any difference. Okay, the plot thickens. So number one, remember how I said I checked all the transistors here on the board and they all tested good. I checked them statically. I kind of glossed over this SPS 1952. And the reason I did that was because, if you recall, on the newer version of the amplifier, they changed it to an MPSA 65. And let me see if I can find that drawing of the amplifier here. Where did I put it? Here it is. So here's the later version of the amplifier, and if you look, they went with an MPSA 65. An MPSA 65 is a Darlington transistor. So I really didn't check this too closely with the meter, because they don't always test out very good. I mean, you can usually check the base to emitter and you should see like the two junction drops and so forth. But anyway, I decided to go back and check that a little more carefully, and to my surprise, this thing did not check out at all. I removed it, and some of you who work on these a lot may already know where I'm going with this, but those of you who don't. So this is a PNP transistor. The base is the middle pin. And if I go from here, do I have the meter in this? Yeah, I do. Okay. If you see, we have a voltage drop there. It's a little bit higher. And then if I go from the base to the collector, there's nothing. And if I switch it the other way, base to collector, there's nothing. So knowing that, I went to one of my component testers. Grab one here. and just kind of stuck it in there just to see where we are. And it reads like a diode, which makes sense because I only read a diode. So then I thought, well, let me make sure that an MPSA 65 is the same as a, what is it, SPS 1952, and in fact it is not. The MPSA 65 is a Darlington transistor, and you can replace that with either a BC 516, which I have those, or I also dug up these NTE 232s, which are a direct crossover. But if you notice, those are Darlington transistors. The SPS 1952 is not a Darlington transistor. And just to prove it, I actually pulled the good one out of the other side and tested it. It is a very standard audio PNP bipolar junction transistor. And it has a gain somewhere in that 380 to 400 range. So I'm going to go ahead and I'm going to replace these. I want to make sure the pinout is correct. I'm pretty sure they have the same pinout as this. And we're going to replace them. And between that faulty transistor for that inverter and the leaky NPN output transistor, all these other ones now I've tested and they're good. I did not remove them from circuit, but they're all situated in a way I can check them with the meter. They're not reading bad as far as I can tell, unless they fail under load. I don't think so. So let's do this and we'll put it back together and we'll give it a test run. Okay, I'm definitely going to have to do some editing here because I forget totally where I left off. It's been several weeks since I've touched this thing, and I should have by now released just a little catch-up video to show you what I've been doing and why I've been busy. But that being said, I've replaced the phase inverter transistor and its associated current source transistor. Those are working fine, and we now have bias adjust. We also have DC balance adjust, but it's wrong. And if you recall, well, if I recall, you already recall because you're watching this, but one of the output transistors had a strange reading to it. When you read it in reverse bias, it read kind of like a diode. So it was bad, and we needed to replace the outputs. So that's where we are right now. We've replaced the output transistors. And remember, looking at the chart for this schematic, they're calling for matched PNP and NPN transistors. In other words, they need to have a matched forward current gain, and that's not so easy to find. What you'll normally find is that the PNP transistor will many times have a higher gain than its complementary NPN. It's just the way they're designed. And so what we were going to do is a little experiment here, trying the complementary pair of the MJ15003 and the MJ15004. And these are great transistors. However, the PNP transistor has about double the gain of the NPN. It's just the way they're designed. So we're just going to see what kind of difference this makes. And let's turn this on, and I'm just going to look right at the output of the amplifier. So let's see where we are here. We should have 0 volts there. In other words, there should be no DC offset, but I have a feeling we're going to see what happens here. And you can see I have about 100 millivolts. Okay. So we're about 60 millivolts of DC offset. Let's see if we can adjust that now. And see, I'm already maxed out. And if I go the other way, that's as low as I can get it. And what I believe, and of course that's low enough that the protect relay pulled in. So this amplifier is working right now. It just has some DC offset, and that's with this set all the way. And I have a feeling it's because these output transistors, you can see on the NPN, I have about 37 millivolts, and on the PNP, negative 37, so that's pretty close, but the whole thing's off. I don't know if that's because of the outputs or because of these new inverter transistor that I replaced. So we're going to have to look in this a little more closely. I do have an alternate set of outputs now that are matched, but I don't want to change those because I want to see just how much it really means, or how much this affects things. Okay, and just as I thought, the whole front end is working correctly. So if you look, we should have about 16 volts, 16.2, 16.4 on the base of the inverter voltage amplifier stage right here. So we should see about, like I said, about 16.2, 16.4. If I go on the base very carefully, 16.27, it's right there. And so looking at the output, that all looks good. And I went through and I checked the bases of the differential pair, and they're both at about a half a volt. And they're identical. I'm not going to go around the camera here. So I really believe at this point that our problem with DC offset is because of the unmatched output transistor. So that kind of answers the question we've been having, is how important is it to have matched outputs? Because in most amplifiers, the output transistors can be pretty far mismatched. Because of the way they're configured, which is different than this amplifier, it doesn't really matter. So if you look here, normally what they do is the emitters will be tied to the center point. You can see they did the opposite. They tied the collectors to the center point in this design. And the way they're, even though this is a 0.15 emitter resistor, you know, it's not real high resistance, this is going to be a configuration where the gain of the transistor is going to have an influence on it. So let's swap these out with something different and see if it changes at all. Okay, so I just want to document a couple things here for this project that we're working on. And what we're going to do is we're going to use the triplet 3490 transistor analyzer. And we're going to put some real world current and voltage onto these output transistors and kind of map out what they are. Believe it or not, this particular device is capable of testing a transistor to the same level that the actual R576 curve tracer can do. The only difference is, instead of tracing out a curve, you actually dial in the different parameters, and then you can record those parameters, like on graph paper, kind of plot your own curves if you want. But this is a great piece of test equipment. Now, I'm not going to use the 576 because it has a couple of problems, as I've stated in an earlier video, and I really need to check the calibration at certain, especially at the higher end on it. I have to make sure the display is working properly, and one of the controls is broken and it needs to be repaired. So I really don't want to push that thing very hard until we get some work done on it. And this is a really nice, convenient way to test a transistor. So we're going to do that, and we're going to use the analyzer, and we are also going to use, just for comparative, we're just going to use one of these cheap little transistor testers that you get online, you know, and kind of see how some of the similarities and differences. So what we have right now on here is one of the original Motorola PNP transistors, and I'm going to turn this on, and I have this set up, And I'll show you how this all works. So essentially you have 3 meters. This one on the left is actually going to show the base current the way I have it set up right now. So it's going to read it right now. I have it set for full scale 3 milliamps. For doing DC beta testing, and this will also do AC beta, we're not going to do that right now. And if you set it to this one, then you can pretty much directly read the beta of the transistor out on this. And this is actually going to show you the collector voltage. And you're going to see that the collector voltage is going to drop down as you increase your base current and your collector current starts to go up. You'll see this drop down because there's actually a load resistor that's in line with the collector emitter junction, and that resistor begins to get more of the current as it divides between the transistor. So you'll see all this happen. So let me turn the power on, and right now we're on the 60 volt range, so I have 50 volts DC on the collector of this transistor. And of course, with no current flowing, the full 50 volts is sitting at the collector. And if I turn my base voltage up a little bit, you'll see this start to drop, or my base current, I'm sorry. We set it to this set point, which is going to be 1, okay? So this is 1 milliamp input, and then this is going to read, we're on the 1 amp scale, so each one of these, it's 100, you know, this is going to be 1 amp full scale, so 200, 400, 600, 800, 1000 milliamps. So if we have 1 milliamp in at the base, and the collector current is, what is that, 300, let's say, I'm looking at an angle, I'm standing way over here, let's say it's 300, then that means that you have a gain of 300 on this transistor. And it's still getting a little bit warm, not too warm, but big huge heat sink here. So the nice thing is you're putting actual current into this. So you can do the math, you're actually putting some wattage in there a little bit. And at the lower collector voltages, you can actually put up to 30 amps of collector current through this thing. So you can really test these out. But what I wanted to show you is, in the manual, they show these transistors as having very low gain, but believe it or not, they actually have pretty high gain. Now, this is a PNP transistor, and if you notice, the PNP transistor was a gain of about 300. Let's switch over to the NPN one now. I'll be right back. Okay, I've removed the PNP device, and we're going to put the NPN in. We switch over to NPN mode. Let's get this plugged in, just like so, if I can find the connector. Isn't this fun? All right, we're going to turn this on. Again, our 50 volts. We're going to leave everything the same. We just went to the different polarity of device. Once again, we're going to bring this up until we get set to 1.0. And you can see this one's a little below 300. It's what is it, 280, 290, something like that. So they're within a beta of maybe 50 or 60 of one another. So they're kind of matched, but they are not perfectly matched. But you can see that's how these transistors are working. Now we can also do some leakage tests and so forth with this, but it's just as easy to do that with other test equipment. Now let's look at our replacement transistors. All right. So yeah, I can feel this is warm, which is great. I mean, it actually puts real current into the transistor. So I want the NPN. I think this is the one, and if it's the wrong one, oh well, we'll learn the hard way. I think the 003 is the NPN. If the meter jumps up real fast, we'll know we have the wrong one in there. All right. Okay, and this is our replacement. This is the MJ15003G. I'm going to bring this up. And you can see this has a lot lower gain than those Motorola's. So when I put 1 milliamp of input current at the base, the collector current, you can see, is less than 100 milliamps. It's maybe about 90 from here. I'd have to get over there and look straight down, but the gain on this transistor is only about 90. Now let's look at the PNP, which is the MJ15004, I think it is. Okay, we have the PNP device in here. Let's bring this up. And you can see it has a gain of about 210, 220, something like that. So this is one of those examples. This is a complementary pair of transistors, so MJ15003 and MJ15004. And you can see, even though they're a complementary pair, the gain is very different. The PNP device has a much higher gain than the NPN, and this is pretty normal. So the trick is, these original transistors have higher gain, and they're more well matched between the NPN and the PNP device. So what we want to check and see now is if we can find another modern type of transistor that will have a little bit higher gain and that will have a little closer match. Before we do that, we're going to do the test on this and see if this agrees with this device when you actually put real current onto the transistor, and see what kind of different results we get. Okay, here is the PNP Motorola transistor, the original one from the amplifier. And you can see it has a beta of 246, which is pretty close. If you remember, we were reading about 250, if you remember. And it was reading about closer to 300. So it's pretty close. The gain was a little higher with the higher current on it. Now let's put the other transistor on there, the NPN. I'll just leave the camera roll while I do this. And let's see what it does. And if I'm not mistaken, this one's a little bit lower. And see, this one says a gain of 68. See that? But if you noticed, when we actually had real current on there, this was reading more of a gain closer to 190 to 200. So you can see how much that can change based upon the amount of current and voltage that you're applying to the transistor. See, the beta of a transistor changes with frequency, and it changes with the amount of base current you put on it, and conversely collector current. So that's why you really can't do transistor matching with these little handheld devices that only put a small base current and small voltage on the collector when you're checking power transistors. It just doesn't work. Now these would be great for small signal transistors, but you definitely don't want to do transistor matching with these on something like that. So now let's look at a different pair of transistors. Okay, we're now going to check a pair of MJ15015 and MJ15016. When I look these up, the data sheets on these appear to show that the PNP and NPN transistors are very similar in their gain range. So we'll see if that's the case on these. And these probably will have a pretty high gain on them, kind of like the original Motorola's. So let's take a look and see what we get. Okay, here's the MJ15016. And if we put some current on this, this is the PNP transistor, and you can see it's about at 220 again, just like the original Motorola. And let's switch over to the 15015 now. Okay. And bring this up. And you can see this thing has some insane amount of gain on it. This is the NPN, which normally the PNP has higher gain. But if you look at this NPN transistor, we're clear up almost to 400. So it's pretty high gain. But these transistors both have high gain when we put some current to them, which is a good thing. And even though they're different, I would have to say that the gain range in these is better than the MJ15003 and 15004, because remember, one of them was very low and the other one was very high. These ones are both high, and that's kind of in the ballpark what these were. They're not, certainly not quite as matched as these, but I think if we messed around and tested several of them, we can probably find a pair that are pretty close, and they should perform in the same manner as the original Motorola's. So that's what we're going to do. And again, if we check these on this, let me do that. Okay. And again, just like it agrees with this now. See, it's showing a beta of 446. So this is really staying pretty linear with base current. And if we go over to this one, $183. So like I said, it's about half. And this one is reading a little bit lower at a low base current than it does at the higher base current. Remember, it was a little bit over 200, about 220. And it's reading 183 with this. So again, I think these are still, we can play around and we can find some that are close enough to still work pretty well. I think these ones being, one of them is like a, 250 to 300, and the other one was reading very low, like, what was it, 80 or something like that. I don't think these would be a good fit for the way this thing's designed. So let me play around with the ones I have in stock. I have several of each of these, so I should be able to find some that will play well with one another. And then we're going to go ahead and get them installed in the amplifier. Okay, so the results are in. For all the NPNs, they all track anywhere from 395. Well, actually the smallest one on this was 380, and the highest one was around 400. So we were in the high 300s, let's say, 380 being the average. All of them, very, very close to one another. And on the PNPs, they started from about 215 and they went up to 240. So those are all in that 220 range. So they are still, there is a gain difference, but the good news is they're both high gain devices. Whereas if you remember looking at the MJ 15004 and 15003, the NPN device was only, very low gain. And well, let's look at it once again. It was very low. The other one was a gain of, was up in the hundreds. But this one, if we look at it, so you can see, yeah, it didn't even have a gain of 100. It was only about 80. So that's where you run into problems, I think, with this Marantz amplifier, is that most of the amplifiers you've seen on my channel, like a lot of the Pioneer and Sansui gear, they all use transistors that are like that, where the PNP is a lot higher gain than the NPN. One of them's a low gain transistor, one's a high gain. Whereas this one, both of them need to be high gain, even though they might be different by 100, 150 or so. It won't matter. It should work, but they just have to be high gain range. So we're going to try these devices, and we're not going to use the 15003 and 15004s. Okay, we have the new output transistors fitted, and we also have the inverter and the inverter's current source transistors replaced. Remember that the inverter transistor was bad in this, and the one output transistor was leaky, and the other 3 were okay. So after doing some matching with these and choosing what we think is a suitable transistor for these, for the inverter and the current source, which is, so we have this one right here. And this is a rather important transistor. It's not here to invert the signal only. It's actually here to give us some voltage gain. So this is a voltage amplifier stage, and it has the constant current source with it. So this is really important. Hopefully we got it right. We have the meters connected. This one here on the left I have connected to the speaker terminals, or to the output of the amplifier. So this is going to read our DC offset if we have any. And this one is going to be the bias setting. So this is just reading between the collectors of the, or is it the emitters? I always forget. The outputs right here. So it's basically going across these 2 resistors here to measure the quiescent current of the outputs. So let's turn this thing on and see where we are. Okay. And looks like our offset is off the charts. Now we did get a protect relay to come in, but we have 700 millivolts on the speaker terminals right now. So let's see, and our bias is not bad. It's low, but it's 13 millivolts. We want it, what did we have the other side set to? I'd have to even look what we calculated. It should be somewhere around 25 milliamps or millivolts or something like that. So let's see if we can adjust this offset. That's the wrong way. It is dropping. And the pot is now maxed out. And I still have 47 millivolts, negative 47 millivolts of DC offset. So something is not correct in here. I can't adjust the offset to 0. The offset pot is maxed out. And just so you see what I'm adjusting here, we're adjusting this pot right here. And it could be that one of these is bad, but I highly doubt it. This is the component we replaced. The old saying goes, show me where you've been and I'll show you where the problem is. So I kind of always go by that. And what might happen, what this may be, is we may have gotten the wrong component in here. Let's talk about that. So if you recall earlier in the video, there are several part numbers that were given for this transistor right here. And some of them cross over to a Darlington very high gain transistor, and some of them cross over to just a standard transistor. And when we measured this one, it appeared as if it were a standard transistor. So, but of course this one was bad, and I pulled the good one out of the other channel, and again it seemed to read like a standard transistor. That being said, we just may have the wrong component in there. It may have the wrong gain. This is where we start getting into all the talk that you read online about these Marantz amplifiers from this era. There are certain transistors in this amplifier where the gain is extremely important. I know people get kind of hung up on saying the word matching the transistors, but again, I keep saying it is more important that the gain is in the correct range, what they recommend. If the gains are all within their proper ranges, the matching is kind of secondary to that, because they will operate properly if they're all at the correct gain. So if you just had a matched set of transistors and they were in the wrong gain range, they still wouldn't work. So that's kind of what I'm talking about. And it's mostly in the earlier stages of this amplifier. So it's very important that we get this inverter transistor and its accompanying current source transistor correct. So let's see if we can measure them a little more carefully and see if we can find a problem there, because I think that's where our problem is. Okay, the first transistor we're going to test is this little SPS 1951. We're just going to use this little tester. And again, this is a small signal transistor, so if we don't need the transistor analyzer to apply high current and things like you would to a large transistor, a power transistor. So this should give us a pretty good indication where we want to be. And that would be this transistor down here, which is the constant current source for that inverter and gain stage. So let's check it. And as you can see, it's just a standard gain, standard transistor. There's nothing special about it. It's a silicon transistor. It's reading okay. It's not showing any leakage. This thing will show a leakage voltage if it's on there, and it's not. So I would not say this one is is a high gain Darlington transistor. And again, the later models of these seem to have a different part number, which I don't have one of those new models in front of me, but it appears they changed that to a Darlington. Now this is an SPS 1952, and that would be this transistor up here. And this is where it gets strange. This is the original circuit design from the first generation of this amplifier. If you go to the second version of this amplifier, they changed that transistor to an MPSA 65. See right there? But this one, very clearly, is an SPS 1952. And these are really hard to get accurate data sheets on. There's not a lot of information out there on them. I mean, even when you go onto some of the forums and things. And you can see this one just reads as a diode. It's bad. So this is definitely a bad transistor. And let's see if we can find a data sheet here. I think I have one. But once again, we just don't know exactly what this is. As I said, I pulled the one out of this channel. It appeared to be just the PNP complement to this NPN down here, which would indicate that it is a standard transistor. And in fact, this one tests as a standard transistor. And the transistor we replaced it with was an MPS 6519, which is the kind that was in, well, which is supposed to be a pretty close match to this one, but who knows. So let me see if I can find something different to put in there and see if it makes any difference. Okay, those of you who may be working on these may want to pay attention to what I'm going through here, because your unit that you're working on may be a little bit different. A lot of what I've done, what I'm finding out through research, is these transistors aren't the easiest things to cross over, because it's really hard to get the correct information on what they're supposed to be. And even testing the other side that's working, I'm still not convinced that everything's exactly as it should be. So what I had here is I had one transistor that is working, and that is the SPS 1951, which is the current source. It was not shorted out, at least from what I could see. It was working. This one is the shorted transistor, and that's the PNP, which is the KSP 1952. And what I've done is I've gone through and meticulously dug through all of my stash and found the transistors that I think are the best substitutes. At this point in time, what I think is the inverter transistor, which is the PNP, needs to be a high gain transistor, and the current source transistor, which is the NPN, needs to be a low gain transistor. Now, finding a small signal low gain transistor is not the easiest thing on earth, at least from what I can see. I've done some reading online, and it seems like some people have had success with a BC547A, the A being the lowest gain range of that transistor. I do not have those. I only have 547Bs and 547Cs. But I did have this KSP42, and I hope you can see it in the camera and it's not blurred out or anything, but it's a KSP42. And for the high gain transistor, which is the SPS 1951, which is a PNP, I'm using a 2N5087. And I did curve trace them, and they do seem to be what I'm looking for this. And again, I could still be wrong. I'm going to put these in and we're going to try them. I just know that the combination that I tried at first does not work. And I don't believe there's anything wrong with the differential pair. Those transistors seem to be perfect. All the voltages around those diff pairs are good. It seems to be that the problem is happening with this SPS 1951 inverter transistor, which is a voltage amplification stage. So let me get these fitted in. They are both direct pin-for-pin replacements. And let's see if our offset is able to be adjusted by doing these two changes. So again, high gain for the inverter transistor, low gain for the constant current source transistor, and we'll see what we get. Okay, I hope I have this all correct in here. We're connected back up, offset and bias, and we have our two transistors put in, and let's see what happens. Okay, we're going to go to millivolts here and go to millivolts here, and we still have an offset problem, but let's see if it's because we have the pot turned the whole way the one direction. So we're going to have to look at this a little bit more and try to find out where our problem is. Again, I think this is a transistor issue with these ones that we're trying to replace, but who knows. Again, the differential pair seems to be just fine in this thing, so I don't know. Of course, I didn't remove them and match them to make sure they're matched, but they're the original ones that were in there, and I don't think that they're bad, but we'll see. Okay, so I've verified all of these voltages, and so far they appear to be good except for around here. These are working good with those transistors I have, but I still cannot get the DC offset where we want it. And the only thing left is going to be these transistors. So I'm going to pull them out, and I'm going to look at them a little more carefully, and if we need to replace them, we will. But definitely, I think we have a problem here. All right, let's get set up here. And I don't know if we're going to be able to see the curves. Let's turn off some lights. Maybe we can get a better view. It's always tough to find a... Okay, there's something. All right, so let's look at the one transistor, and you can see it's just above that top graticule. And you can see that one's a little bit less. So they're not perfectly gain matched, but yeah. So let me put them on the little transistor tester, and maybe we can find a little better matched transistors than that. Okay, let me put my mic on here. So looking at these, the VBE is a little bit different between them, and the gain is different by about 50 according to the little transistor tester as well as the curve tracer. So they're not super well matched anymore, and that might be part of our problem. So let me see if I can find a suitable replacement, and we'll get them in there. Okay, I found a pair of MPSA 18s, and they're high gain. They're around an 800 HFE. There's one. There's the other. They're dead on top of one another. So they are perfectly matched. The VBE is matched. Even if I use them on my little matching jig, they're perfect. So I'm going to put these in, and we're going to see if that improves our situation. Okay, our matched transistors are thermally coupled and they're installed. The amplifier is turned on. And look at where our... yeah. And the potentiometer is right at the center of its travel. So it turns out that these transistors drifted a little bit in value, and they did need to be replaced. Okay, we have a signal and a dummy load connected. Amplifier's warmed up. We have this set around 20 millivolts for the bias. We have the offset down in the single digits of millivolts. Let's put some power to it. And that's about 12 or 15 watts right there. Let's kick it off. This should return back down towards 0. This should drop back down to 20, and it does. Very good. So I would say we've repaired this amplifier. It is working now. Well, here we are ready for a audio test. And I can tell you, I just did a quick bias set on this thing, and I can feel this heatsink is actually warm, like it's not room temperature. This one is almost at room temperature. So I know this one's going to need to be adjusted. It's not hurting anything, but it's just, it doesn't need to run that warm. This is the one that we replaced all those transistors in. Down here is what we actually ended up replacing. And it was the inverter transistor, which is this one right here, the associated current source transistor, which is this one here, and the two differential pairs, and these were not matched anymore. They had drifted out of tolerance, which was one of our biggest problems. And if you recall, one of these 4 transistors was leaky. The other 3 were okay, and they probably still would have worked, but I would imagine that this one would eventually have failed the rest of the way had we not replaced them. So we replaced the outputs, that inverter driver right there with its current source, and these 2. And that's it. That got us back up and running, and we also, same as the other side, had to swap out that 220 microfarad capacitor, which is right here, and that has to do with our bias circuit. It was all leaky. So we're back up and running. Let's play some music and see what we can get. Yeah, so it sounds beautiful. Now, don't pay attention to these meters. They are really roached up. We need to completely rebuild that. This amp is going to need to be rebuilt, but what we wanted to do is we wanted to get it to a working order before we do any kind of changes or anything. And we've done that. So now we can go and break down these two amplifier modules again, kind of replace some of the components we wanted to replace. We did do a current source mod on the left channel. We're going to do that same thing to the right channel, get everything balanced, and then we're going to do a lot of testing. But that's going to be for the next part. So we now have a working amplifier. It sounds good. We saw what it's capable of doing on this channel when we tested it on the last video, and we're going to get the whole thing working that way. So we're going to close this one right now, and when we return, it will we'll be working on another soldering chat. So for those of you who like that, stay tuned for that video. Those of you who don't, the video after that is where we'll actually be doing some real testing on this and seeing how well it performs. Until then, I wish you all peace, joy, happiness, and good health in your lives. And thanks for being patient and waiting for this next part to come out. It's been very busy at work, and it's still going to be very busy for a little bit of the foreseeable future. But busy is a good thing, you know, especially in these times. So I'm thankful to have the work that I have. Anyway, you all take care, and we'll see you again real soon. Bye-bye.